to the fresh engineers, right? However, I think this one is kind of like give you the ballpark. It's not very detailed because we don't have much time, and I think the focus of you guys is computer engineering. So VLSI is currently taught okay in the US for both computer engineering and also for the double E, electrical engineer. So the reason for that is because semiconductor, right? VLSI design is produced not like it's made not by only the electrical engineer, but it also need the software skill. So that you see that like I think yeah, I just from the computer architecture, you see that like hardware and software has equivalence because of cost and performance, that we have to like a balance between like you have, if you use more hardware, it will run faster, but in the case you don't need the performance, you don't need to run fast, then you can put a lot of software, right? So let's say like to do like a plus b, then you can have an adder. Instead of using an adder, you can use a NAND, NOR, and NOT to make a circuit to replace the adder, which means like you can use the adder as the adder in software, or you can use the adder as in hardware, right? And you can see obviously that using the hardware will be faster because using software it need to be broken down into like the primitive steps, and then it will be executed consequently, and then like you see that it will take time. So the reason to take the software if you don't have any concern about running time. And the reason, and you have to balance between like the that's about like roughly about the speed and the cost. Running software, it will be much like cheaper than if you put in the hardware. Now the answer of that is this. So you have this one is a whole picture of the semiconductor business and the terminology. So the purpose here is to introduce you guys to like what is a VLSI industry. And the second is you learn all the terminology related to this industry, so that like you know what does it mean. And the simple thing is a VLSI stuff, and then like going forward you will have some like kind of like a slang or like ECO, like a PT, like yeah, a lot of slang like floor plan, place and route, timing closure, and so on. So you know, because from like the beginning, right? But so you will see like you will understand the development methodology and the flow apply industry. So we talk about in detail later, and comprehend and practice the background. I think I remove the detail because we have no time and we have no tool to do the detail. For each major phase of LSI design, LSI design flow has about at least like a 10 small steps, 10 major steps actually. So we cannot wait like a 2 hour a week, 2 hours a week, and then 15 weeks, we have no way to be able to achieve it. So the next one is this one I consider that is the most important for you guys to learn from this class. So based on what I learned and work here in like in the like industry, like a semiconductor industry, and the way people work here, I try to convey my knowledge to you guys so that you can understand how people work here, how they interact, how they work like in the team, like at a vertical and horizontal way. Vertical means that you work from like okay, from the relationship between the boss and the employees, and then horizontal means like between the teammates, and interdiscipline means like between the team to the team. That's a very like a lot of respect between people. But okay, I will introduce that along the way when I have time. But it's not really like those things is for your knowledge. It's not for the exam. Intended audience is for you guys. Okay, So the whole class has 6 chapters. So the first one is the first one that we will have we'll go through today is introduction to the LSI development. So this one is will it's kind of like introduced to you the ballpark of every step. And then the second one is the logic element and the electronic the signal on silicon. This one will go to some okay. So I think we go to some like detail about like transistor, but I will reduce that. You have the slides of the transistor, quite a few, maybe 20 or so, but I will reduce that like because you don't need to know much about transistor. You need to know about how the logic gate works, but about the transistor is quite we waste your time. We will take that time to do something else. The third chapter is about LSI logic design. So this one is focused on the synthesis. I think in the lab there will be like one lab about the synthesis. So that's the synthesis design, logic design, or like equivalent to a synthesis design. However, in that we will have also the verification. So verification will be applied in the logic design. It's also in the physical design. So after we have the synthesis, I think we will go to like do the synchronous design and then learn about the STA. STA means static timing analysis. So there's a asynchronous and synchronous design. Synchronous means the signal every change. I think you can learn about like RTL. So you know that like there's the synchronous, right? So which means that at the positive edge or like a negative edge of the clock, everything will happen, sync up together with that, and then everything happen and it will pattern or be sampled to the next stage by the clock edge. The chapter 5 will be designed for testability, DFT. The reason for that because when we design, we need to know if it works first and it works as expected. So this one is like we have to test it. It's that's the job of the verification, right? The job of verification is to do like a verification, but this one is for testability, which is that the tool need to be able to be tested, not just that one we design and then we just like okay here's my design, but now the guy do the test like the testing engineer, they need to know where to test, and they need to like they need to have a mechanism to test the logic like let's say you have an input and output, right? And then if you just like put the input the input vector and then you check the output vector and you see that oh it's not as expected, then you have nothing inside, so you don't know how to like where's the bug. So which is I think that's why they have to introduce, they have to insert the logic or like the logic for the test. They call that like um, they have the scan, they have the flop like and they have the logic to test inside the design. The last chapter is the layout design. Actually, layout design is maybe like misleading. The main like terminology that people use here is basically is a physical design, which is a PD. It's like to differentiate from the chapter 3, which is a synthesis design or logic design. The chapter 3 is maybe equivalent to like RTL or something like that. So nowadays, in the old days, LSI logic design is separate from the physical design. First of all, I have to explain a little bit about physical design. Physical design, it means that after you do the synthesis, you have a net list, which means that the list of the nets, which is the list of the component of the design and already design how those components are connected, right? Let's say the very simple design is like you have a NAND connecting to a NOR, and then like a two NAND connecting to a NOR, for example. So that design will have you can see that have a 1, 2, 3, 4, 5 net. One net is output, No, actually it's a 1, 2, 3, 4, 5, 6, 7 nets. One is for the output, two for the intermediate, and four for the 4 inputs of the two NOR input, right? I have two NOR connect to like one NAND. Then I have I have 3 components. I have 7 NANDs, and I have to explain. I have to like describe the connection from like the NAND one to the input one of the NOR one to the input one of the NAND output, and so on. So it's explain the connection between the component. We call that the netlist. And because the component of the netlist is the gate, logic gate, we call that the gate netlist. Thus, the gate netlist is the result or the output of the LSI design. Take that netlist, it go to the layout design, go to physical design, and from there we will do like we will place that into the silicon, and the output of that it will be so now it become like you need to be aware of the physical location of the cells and then on the silicon. That's why it's called physical design. There's a lot of aspect for the physical design. It is composed of the stages like floor planning, place CTS, which is a clock CTS, clock tree synthesis, and then and then there's another step is a post CTS, because CTS is to build the clock tree, so that like the clock tree, right? So because we need the clock tree to provide the clock to every flip flop. Then after you provide that clock tree, you need to do like a post CTS to do like to meet the timing. And later you have a route. You route the design, which is route means to put the metal down to connect between the output and input of the cells. And at the end, you will like optimize that route. It calls post route. At the end, you will export the result, and then it go to like the foundry, and then that's all. So that's like that's all we will go through during our 30 hours of the class. So I think now we will go to chapter 1. What is it? I think. Yeah, okay. All right. Now we change to the next one. Here. Okay. Within this chapter 1, there will be like a 4 bullet or like a 4 like a sub-chapter. The first one to introduce the product, the semiconductor products, and the development flow, and the design flow, and the last one is an example. The example will be, I think, it's about like an RTL description. So because you guys already like took the course of RTL, so I guess like this one you will like look at that, because this one is just an example. You look at that to see how it goes, but I think we have nothing to do with that, because this chapter is only about introduction. Here, product. So I think for the semiconductor is everywhere nowadays, right? So even like you see like the refrigerator, the fridge, it was like basically it's electricity, but later on they will put a lot of things in there. So now it's become smart fridge, because now that becomes a hub for the whole like a smart house, right? They try to do that. And even like a simple thing like the faucet, right? The faucet, now they put some semiconductor in there with the sensor, so that like they can just like do that, water come out. They do one more time, toggle, shut down the water. And then I think even like in the bed is just wood, right? But they will integrate also some like gadget, the electronic gadget, so that like they make the bed has some feature, and then you can imagine whatever you will see that like provided that there's a demand, there will be the product for that. And then now I come back to the picture. So this picture is kind of like a summary and is quite missing a lot of things in here, right? You have PC, that's normal. I think it's whatever. Mobile is also like you see that the car, actually now the car is like one of the two most developed, like on the way of development of like introducing the new high tech is car and the mobile. And also like the is in life, which is in the healthcare. I think for the mobile, we have 5G, right? 5G is now is like in expansion right now. And 6G now is they started to like develop the 6G already. So we have a 5G. The reason that 5G now happening is because of the LSI. Yeah, because the technology is evolved in a way that like exponential. You see, it's exponential like explosion. So you see, like one example for this is, let's say, in the 1980 something, we have the first PC, which is let's say make it like 40 years ago, and now at the time, the number of transistors for the CPU at the time is about 100,000. 130 yeah 130k, let's say make round it up to 100,000 transistor. Nowadays the newest like i10 the iCore, right? The i9 is about I think 5 or 6 billion, and the Qualcomm SoC is about 15 billion. So you see, if you just take that, it's about I think I forgot how much, 100,000 times, right? Yeah, about 100,000 times in terms of number of transistors. So the because of it, you can see that like the power of the calculation of the compute increased that much. So because of that, AI was developed in the 1950s, 60s started, right? But only when we have the semiconductor, like the new chip, the very advanced chip, that AI become reality. So I think, and then I think of with this, I think there's also, I think if you hear about like a metaverse, which is introduced, okay, the term is introduced by like a Facebook, and they changed the company from Facebook to Meta. But metaverse is like they imagine, they envision actually people will live in a world where they use like AR and VR, which is a virtual reality and augmented reality. Then people like live in that. They don't need to live in the real world. I think it's really scary, but I don't know if it's good or bad. But it's really scary, and even I don't like it, but I think it will happen. The next one is okay. I think I should say, for example, it's another field that very promising is the healthcare. The healthcare, so you can see that the pacemaker is like was developed long time ago. The pacemaker is the device that they put inside the body next to the heart, so that like it will keep the heart. You see that people have the problem with the heartbeat. So the heartbeat is not in regular rhythm. So because it beat like sometimes too fast, sometimes too slow. Because of it, sometimes it can kill people. So they put a pacemaker to keep the heartbeat in regular like a frequency. So but that is like a really like long time ago, maybe like 30, I think maybe 30, 40 years ago. And then now you have like there's a like what a major here in the engineering school, which is called BME, Biomedical Engineering. That one is like to try to like make people like a cyborg, which is a cyborg is a human with a lot of electronic and help people to perform way outside of their capability. If you know about the skeleton, right, the exoskeleton, something. So even like a very small people or like very weak people, when they put in that like a clothes, right, that like equipment, they use that as they like the power of the arm or like the leg or like whatever. So something like that. But not only about like the raw power. It's also like Facebook is currently on the project that like can make the blind to see. So they are on the way. I think the project was announced I think maybe 5-10 years ago, and now I think they are close to that. They claim that it might be available like within 5 years. So like so that people can see. All those things is semiconductor. Next one is I think is like you have a consumer electronic. Don't need to talk about that. It's obvious with yours like whatever like video game stuff or like okay. I don't think I need to mention anything here. For the agriculture, right? Agriculture, I think even that now is like modernized with the semiconductor. Oh, there's another one. It's a national security. You have the robotics. You have the AI, right? AI, I think you know well about that. And you have energy efficiency and quantum computing. So everything like a moving forward, semiconductor and software is the center of it. Without the semiconductor, software cannot go far. And without the software, the semiconductor is just a core, a body without a life. So these two will go together. And then, as I said, software and hardware go together, and it's at a balance that I think always like when it's involved, it's just like evolve like it will have always have the negotiation to find a sweet spot, which is the best performance with the lowest cost. That's the like the reason like these two like go together, and then it's always like they have to work that way. So this product, I think this one is a simple one. They just like the semiconductor products, they divide into two. You have a hardware product, but it still need the software, right? As I said, you have the hardware, but you need the software to support it. So this one is like the soul of the hardware, of the body, which is a hardware. So the hardware product, there's a two product. One is the semiconductor itself, and also you have the emulator, evaluation board, and then like a testing platform, and so on. This thing. And then go further, you have a discrete and integrated. Discrete, like you have a diode, you have a transistor, LED, and so on. This thing is quite the thing is this thing is very annoying in a sense that it occupy a lot of space. You can see that, right? The LED, but without that, but those things need to be there to provide the communication like, or the interface with human. Transistor here is used to drive like the power transistor or something. So all the like, but it's kind of annoying because at the scale when we have okay, let's imagine it's an IC. It uses the transistor, the mass at the very small one, but this one is very big. This one is in the size of 4 nanometer gate length. And if you take the whole transistor, it's about maybe like, let's say 10 by 10 is 100 square nanometer. 4 is a 12. This one is a 5, 12 by 5, 60. Let's say, okay, put it at 100 square nanometer. This one you can see by itself. The diode by itself is in the square millimeter. So square millimeter versus a square nanometer, you see how much is different. That's why This one is need to be like reduced. So you see that in like if you open like the Samsung mobile phone, right? The Apple, you can open that. You can open the other one. You can see that there's a board, there's an IC, the big IC, and there's just a little bit of like a resistance, cap, capacitance, and the LED here and there, and then connectors, those kind of things. Analog and digital. Analog one is like a kind of compared with digital is quite like from the discrete compared to integrated. This analog guy, you like you have the antenna. The antenna can occupy like a surface area easily in the sense of let me say the ballpark of 1 square millimeter easily. So again, 1 square millimeter you compare with like 100 square nanometer, and yeah, you have some like idea. Let's go to the next one. So here they classify the IC. So in the old days, we have in the very old days when I think I used to work at TI. There's one employee, like one person is very famous in TI. Unfortunately, I just forgot his name. Sorry, but he got the Nobel Prize because he's the first one. I will tell you like the name later. He got the Nobel Prize because he's the first one who did the who like succeeded in making a integrated circuit. At the time, he just integrated circuit means like you integrate a couple transistor together on the same die. Die means like the same. You know the integrated circuit has like the substrate. So when you have the substrate in silicon, you connect the transistor in the same use the same silicon substrate. That's the integrated circuit. And it doesn't matter of 2 or 3, provided it's a 2 above 2, it's called integrated circuit. So that guys like make it happen. The first one that was in the I think 1950 58 I think. So because that's the beginning of the era of integrated circuit, thanks to that technique or like that development of the integration, that now we have the integration of like a billion of transistor. So he's well deserved of that Nobel Prize. So we go like you have like SSI, small scale, which is at the time like a couple 20, 30 or 100 something. Then they go to like MSI, LSI, and so on. The size of that is very like vague. So I think you don't need to care about like what does that mean. VLSI is a very large, ultra large. You don't need to know like how many transistor because it's just meaningless. Just know now that VLSI or USI people don't use that much. They just use the LSI or like basically use a VLSI. Because the VLSI or USA at the time, maybe 5 or 10 years ago, it's only like a million transistor. And now it increased by 1,000 times. So they run out of the description, so they should stop at like they should go back to VLSI or just maybe like just LSI. All right. So in classification in terms of integration level, so they have a SoC, which is called like a system on the chip. You need to understand like what is die, but I think we will learn that later. So let's like briefly let's say like this. You have a CPU, right? You have like the I-core like i9, i7. Is a CPU like that? It will be sold as a chip, as an IC. And then there will be like a memory. There will be like a DMA. There will be oscillator. There will be VCO. There will be a lot of kind of semiconductor chip. Now, instead, if you have that separate, then you have to connect it in the PCB, like a printed circuit board. You have to connect it by the metal on the PCB. So if you connect it that way, then the problem is like the problem is like you have the delay and the speed, because when there is the connection, there will be delay on that connection. When we talk about delay here, it delay here because the circuit, right, run at the gigahertz. So gigahertz means the period is only like a 1 nanosecond. So that means it's not every second counts, but it's every picosecond counts. Because when you have the period of 1 nanosecond, it means that in that you have like a 20, 30 like logic on the same path. So it's okay. So I think to achieve the 1 nanosecond period, you have to count, you have to like calculate and then like make every picosecond count, so that you can like that's like a finer granulation, right? So that you can achieve a nanosecond like a target. If you go to like a terahertz, then you have to go like a femtosecond, right? But right now we are at the gigahertz. The fastest chip currently is about like a 5 gigahertz by AMD and like Intel, like the CPU. So because of it, like when you have like between like you have a one chip is CPU connected to like the DMA and also the memory. You connect that, and then you have to use the PCB. It will, because you have to use the metal to connect that, and the distance between them at least 1 or 2 centimeter away. So it can cause you like the delay of like 1 or 2 nanosecond. That's why they have to use a system on the chip. Like instead of putting each block like that separately, it's on a package. They put all those blocks in the same chip, which is using the same die. Now you have the CPU, you have a memory, you have a DMA, you put that in the same. So it's called a system on the chip. So you don't need to have everything in a chip to call SoC, provided you have only 2 blocks and plus. It's called system on the chip. Because some guy will put like only like a DMA memory and the CPU. That's the one kind of system on the chip. The other guy will add the I/O. You have another one. Qualcomm has also like a CPU memory. You have a L2, L3, and then you have also like they put also like the modem in there. So there's also the system on the chip. So system on the chip doesn't mean they have the same component. Just you have a two block in that, it becomes system on chip. The reason for that is for the signals to traverse to go across the chip quickly. So the benefit of that is the performance, and also is about the real estate, which is the space. You imagine that you put like two chip, right? Two IC on the board, and then you put only one. So if you put only one chip, it means that you have like the space will be reduced. And then you see that like on the phone, right? And the mobile phone, you have only like a very small space to put things in. So if you reduce the number of chip, then you can use that. You can like reduce the size of the phone, which is like a minimize of that is like the goal. SIP, like a system in package. So now we have let's say like they run out of when they put like a lot of block in the same, they have a system on the chip, but they cannot put everything on the chip because it's too much. The chip is becoming too much. Then they have to like partition it into like a multiple SoC, and they put that in the same package. So the same package, but actually there's a multiple chip in there. The connection between them will use the Y or like whatever, like there will be terminology for you to learn later, but I don't want to like inundate you with too much thing. Functional characteristic, you have memory device, you have logic device, you have all kind of. Now I think this one is important. Classification of IC from the viewpoint of like a point of view of user. So this one is for you to recognize. Standard product means like off the shelf components. You can buy it like a DRAM, SRAM, FPGA, and so on, right? At my time, it was like we can buy something like the BJT logic using like a I think the series I still remember like a 7400, 74LS stuff, and so on. Then you have a DRAM, SRAM, FPGA. Those things is a standard. You buy it and then you just plug into your circuit, and then you use the software to make a difference. But the difference is when you do this one, the software is a difference, and also like the design too, and you how you connect them will make the difference. Now this one you have like a go another like a go to work like a little bit more like customized. So you have a DSP, which is a digital signal processing, and then you have an embedded time microprocessor like a microcontroller. Microcontroller is the kind of SoC but small one, which has like the CPU, a little bit of memory, a little bit maybe they don't need the DMA, maybe they have a simple DMA, yeah, and then they have the I/O. So it's kind of a system like on a chip, but a very small one and simple one. The purpose of the microcontroller is called, okay, let me put like a MC. This one is the MC here, like this one is used actually like a test instrument make money a lot by designing this thing, and they sold that to industry, because in the industry, right, when they have they don't need the laptop or the desktop to control things, because the laptop and desktop is a universal, so the program, it would be like cumbersome, the program would be like you will need to run a lot of things. Now here, if they want to control like some like a chain of production, like go from A to B to C to D like that, then they have a specialized program, and the requirement or the need for them is just as simple. So they just use the microcontroller with a simple specific program plug into the microcontroller to control their product, their production chain. So that's how why like you have that. So they will buy this one. They'll buy this one, but still this one you have a lot of kind of MC here. But this one still like will work differently by the program they embed it into that. DSP too. DSP like you have a lot of DSP like DSP for like it depends on your purpose that you use that as like somewhere that you don't like you use that for the battery based device, right? A device that has a battery, it need to be like a power efficient. A device that is plugged into the outlet, electrical outlet, it doesn't need that, because the outlet provide like whatever like electric power you want. So which is I think you see that like for example a simple example is the laptop versus the desktop. The laptop, they need to save the battery. Even the battery of laptop is too big, but that's one example. The same thing with the mobile. But mobile has like a lot of requirement, not just the power. The last one is the ASIC. This one is a die down, kind of become like not very good. It's no life ahead. The reason for that, like nowadays, I think people go to like the fabless, way. I think I will explain later. The ASIC is like a company has a spec, has the requirement. They have have a product, right? They have a product. Okay, I will actually I will explain later. I think it's yeah, I will explain that later. What is the ASIC versus this thing? So this thing will be explained later. Now, this picture describes the whole process from like the beginning until the end. The beginning of how a product is made until like the end when you have a product on your hand, which is like it starts from here. This starting point is here. Then this one is like a two-way street, not a one. Let's say like you want to make a product like you want to make a product, a selling machine, right? A selling machine. You want to sell you send your Coca, sorry, the apple juice, orange juice, or like sparkling soda, and so on. Kind of like drinks, soft drinks. Then you will have that. Okay, what is like you have input and output. Input is 5 cents, yeah, $5 you have this, $1 you have this, and you push this button, put that button, and so on. Actually, whatever you have the requirement here. But that is like too simple. Okay, I have to make that. Okay, a real example, like now Qualcomm want to make the new Snapdragon. The Snapdragon is used inside the mobile phone, right? For Samsung and as well as for like a lot of phones right now. So Qualcomm want to do that. So it will have the requirement, which is this. Let's say like right now, I think the new product come out is Snapdragon generation Snapdragon 8 and generation 1, Gen 1. The previous one is 888 AAA. So let's base on that AA, they have let's take it as the performance. We have a PPAS, power, performance, area, and cost. Let's take that one as the baseline. Then now Qualcomm will want to do the next generation. They will be based on the previous generation. So let's say like with the performance, I make up the number here because I cannot tell you the real one. So let's say that the previous one is a 2 gigahertz, like as a bottom line, as the frequency of the chip. The power is like a 5 watt. The area is 100 square millimeter, and the cost of each is about, let's say like $1. Okay, that's a makeup number. Okay, it's not $1. But I have to say that because I'm not allowed to say the real one. So with that, now when you have this one, you have the spec. Then you take like if the version of last year is like a 2 gigahertz, then I want to make this year run faster at 2.2 gigahertz, right? Or I want to make it like a 2.4 gigahertz, which is a 20% faster as usual. So the usual one, like in the industry, is that that means that there's some kind of like entitlement here. The next product supposed to be like supposed to be improved versus the previous product by a certain amount, and that certain amount is kind of like standardized. Since a while, the improvement in the performance. When I said performance, it means the frequency. The improvement in the performance over time in the old days is about 20%, which is if you go from the let's say that you go from one product to the next product. If the previous is 1 gigahertz, the next product is supposed to be 1.2 gigahertz, and the next will be 144, and so on. But okay, let's make it simple. It's a lot of things, but let's make it simple. So now I think previous one is a 2. Now this one like let's say like 2.4 gigahertz, which is 20% like faster, right? I take that requirement. I go to the here. Here is the right here is the foundry. I take that requirement. I go that and I ask them like, can you make it? I give the requirement to them, and then they will see they will, and then the basic characteristic or like basic factor from the foundry will be the speed of the transistor. Two things. Actually, the foundry has a two main or like a basic performance or component. One is the front end and one's the back end. The front end for them is the transistor performance. The back end, which is the interconnect, which is the metal to connect between the transistor. So they will look at the transistor and the metal. They look at that, they see, okay, they also have their own entitlement. So going from one technology to the next technology, usually in the old days, they have about like a 20% improvement in transistor, right? But the thing is like improvement in transistor doesn't mean improvement in the device here. It's not equivalent. There will be some like a conversion to make like a 20% here. It go to here, become like it can become like only 10% or 15%. So they get okay, just for so that like it's not a one-to-one. Like they improve the transistor performance by 20%. That means your design will improve by 20%. It's not. The second thing is like it will be the backend for the foundry, which is the interconnect. Usually, interconnect will go opposite to the transistor performance, because when you go to the next node, usually you get like a minimize, right? You just reduce the feature, which is like reduce the width of the wire. Because you reduce that, you imagine like the resistance is proportional, like is reverse, right? Reverse proportional to the profile, to the area. So which is if you have the width of the wire is smaller, then resistance will be increased. If like the width is reduced by 0. Like 50%, then the resistance will be increased by 50%. But it's not only that, because if you reduce the width, and usually the thickness will be reduced too. So if the width and the thickness of the metal reduced by 70%, then it means that like okay, I said it again. If the width and the thickness, each of them reduced by 70%, that's the scaling factor from one technology to the next technology currently. So if you do that, instead of get 70, you get 70% reduce in permittivity. You got like a 50% reduce, which is the resistivity will increase by 2 times, right? So you reduce by 2 times. But if the width is reduced by 70%, then the length will be reduced by 70% too. So which is instead of, okay, if you can see that the same y in the previous generation, go to the next one, it will be reduced by length, it will be reduced by width and thickness. Take all the three together, the resistance will be increased by about like 1 over 0.7, which is about 1.4, right? It's a 40% in about 40% like increase in resistance. Resistance increase, it means a delay. So that means that delay increase, it means reduce the performance. So you have two things that go opposite. One is the transistor is going faster, and you have the resistance going bigger, which is a delay, right? So which is now you have to make like the transistor is not only increased by 20%, but it need to be increased by maybe 30% or something to make up for the resistance. In the old days, the wire is not that long. It's not like the delay from the wire, even like it increased by 20%, but the portion of the delay, wire delay, is only like a 10% of the total delay. You see that? Total delay, cell delay is that much, wire delay is that much. So even this one increased by 100% is still small, right? So that's the old days. Nowadays, because the thing is like a very like the wire is a very like a narrow, and the resistance increase to like you can imagine is that the thing is about 100 ohms per micron. The length, if the length is only 1 micron, the resistance already like 100 ohms. Because of it, it take into a picture of the thing. Okay, then I go back to this one. The thing is here like so that means there's a big negotiation between these guys. I have entitlement, I have requirement here. I go to this guy look at like whatever they can, and they have to push back. Okay, you want 20%, but our technology cannot meet it. So there will be like a negotiation back and forth here until like they settle down. They settle down on a ballpark number, not really exact, because nothing is done or nothing is confirmed until like the end here. LSI product come out. So they will meet like okay, they will sign a contract, say that okay, I will provide you this and this and this. There's a list of requirement here. Then they will like start the process design. These three things will be provided by Foundry. So they will like they will have the process which is all I think you can say that like they said, oh, the 4 nano, you can hear like a 4 nano technology that is talk about the process, 4 nano 4 nanometer technology. Then the device design here, it means like they design the transistor. So the transistor, which is in that there's the parameters like the basic parameters will be width, get length, and the width, the get length, yeah. And then like there's also a lot of things that they design for the device, which is like the porosity, the impurity, all kind of thing like related to chemistry. That like here when they do this one, a lot of things that the chemical engineer involved in the foundry. Once they okay, they just step up, right? Once they finish design the transistor as the atomic, right? Atomic step or the atom of the circuit, they will keep like go to the circuit design. The circuit design here, which means now they design the NAND node. They will provide the NAND, the node as the component. Then when they have a library of the component as a NAND node, exclusive or exclusive node, the multiplexer, the whatever, they will hand off that to like here is our work of the design house. So the designer take that, go through this, and then the output take from here. And now here, it's a spec. After they negotiate, they agree with something. Now we have a spec, the real spec, like instead of 20%, we have the design now it's only like a 15%, right? Something like that. We take the requirement here, we take like whatever like the foundry give us here, we design it. The output of this is like the data for the fab again. Go back to the fab. Sorry, the foundry or like the fab. Foundry or like the name, they can use the fab. And then this one, they will do they will like make the mask, they will do the test, and they will like cut it and put in the chip, put in the package, and then like a test, and then we have here all the thing here. What we will go through is this portion only because this thing is provided by the foundry. This also foundry. All we went through is this. This thing is like I think there's a special team to do this work. They will have to do like yeah, I think we put it here. B B A S. So they will negotiate, I think, performance, power, area, and cost. Cost is come with the S because if you have that, right, you have this one, that's cost. The dollar is cost, but then they put that it doesn't look good or whatever. They usually they use like a PPAS. Now this one is the total LSI design flow, which is in this portion. This portion is the foundry. This one, I think we might not need to. Yeah, we might not need to talk about that because let me see if we need to. Yeah, I think I already like explained to you what's the device, circuit design, and so on. So after they do that, they provide these two things. They provide two things. So these two things is one is the rule and one cell library. Cell library here you have like I will explain later. It's too detailed. I will explain later. But the thing is, we will learn like basically is here. This is our job, and our job basically is here and here. The task we want. Yep, these two things I think we'll focus on that. Mask making here is actually this one is at the Fab 2. Okay, this one is a good one to explain, but I think we take a break now. And then if you guys has any question, don't hesitate to ask me either by raising hand or by put a question in the messenger in the message. And remember, I think I think I just like observed that like um, our culture. I think people talk about a lot about that. The student didn't communicate, like didn't like ask a lot, like very little. But I remember at my time, even at my time, 40 years ago, yeah, 40 years ago, I did ask a lot of questions to my professor, my teacher at school. So don't hesitate to ask if you have any question. That's the way so that you can dig into like no matter what. If you don't understand, just ask it. Because okay, you pay a lot of money here, right? So don't waste your money. Try to use that and try to like understand, learn a lot from here, right? And my purpose is not that for me it's not like about I want to make money, but I think because you pay money you need to like be aware of that. Then then I think I hope that you can learn something from here so that you don't waste your money. Okay, so take a break now. I think Professor Ten, I think we take a break of 10 minutes.
Yes, around this.
Okay, thank you. Yeah, and any question try to, yeah, whatever you can ask me. And by the way, you can ask me by like send me email. I think you have my email, right? I think Dr. Professor Ten has my email, and then I think he will like send that to you.
Yeah.
Okay. Okay. Thank you, Professor Ten.
Yes.
Mm. Okay. Let's see. I will be using this. Okay, I think I will answer the question by talking rather than typing because it's quite a long answer. Okay, first question. First question is which aspect will determine the maximum clock frequency of a chip? So when you have an RTL, right? You understand RTL, which is you have the register, and what you do, you will like have the data path between the register, which is between the flop. So the logic portion between the between the flop will determine the maximum clock frequency, because the clock frequency will be defined as a 1 over the period, and the period is just the delay of that data path between the flop. So did I answer your question, Trung? Does that answer your question? Okay, good. Now the next question from Bao. Okay, so after we use a Verilog in the ITL stage, we will test its use in the text bench and how we can transfer that Verilog code into the wafer. Oh, that's a very long stage. So you can see that like in the presentation like previously, you go from RTL. I think it need to go from RTL is the description of the design. Then you will go through like the synthesis. From the RTL code, you will go through synthesis so that you get the get netlist. And then not only, I think you test, when you test, you using the test bands, you test that that's a very primitive testing to make sure that the RTL meet the requirement or like meet the functionality that you expected. So that one is like nothing just about functionality. There's nothing to do with timing, with the cost, with the area, with anything. It's just at the RTL stage, what you test with test bench, this thing is just primitive again. So you have to go through like a synthesis, and then the synthesis to do what? To like transfer that to the get netlist, and in the mind with the target is to meet the performance, which is to meet the maximum frequency, right? You want to have a maximum frequency is a 2 gigahertz, which means the data path need to be like 2 gigahertz is a 500 picosecond. So from like where you describe in the RTL, it's only like it's described like in the data path between the flop. So there's no optimization. The optimization will be involved with the minimization of the logic, and then after that it will like minimization. I think it will try to like collapse every logic into like the sum of product, or like the product of sum. From there it will do the factorization, and then after that it will like try to map that into the cell library. So all kind of thing it will be like executed during the synthesis. So after you do that, you have the get netlist. Then you print that get netlist. You go to the physical design. Physical design, you have to place. There's a steps like floor planning, place and route, and so on. You go through the physical design, and then you will have it will come out. We will have like something like a file which has contain the information about the mask, but it's not a mask. So the file will have a 1001 digit, whatever the format that the file will have it. And from that file, they will make a real mask. And that mask, you remember like how that you make the print and the PCB, right? The PCB, you apply the mask on the PCB, you get the like acid, the acid to like polish that to like what to make the circuit, the connection. This one is the same thing, but instead of using like they also use acid and also some kind of chemical to grave into the silicon, the same way as you grave into the PCB. So with that, you give that to foundry and you take that, make the mask, put on the silicon. They have about like hundreds of masks, so that they can make a chip, and that's how they. So your question is a simple question, but the answer is very long. So you got some idea about? Okay. The next one is a high. Is there any difference between LSI and SOC? LSI is the superset of SOC. LSI means like everything related to like a semiconductor is LSI or like VLSI. SOC design is just like you have one subset of that, which is like you have system on a chip is also LSI. You have a SIP is also LSI. Like in the previous one, I think the previous line I already answered that. All right, I think we can go back to the class now. Here is the model, the business model. The development, we have two things, the development and the business model. The business model is like you see that is this in is a business model, and the flow is like what is in the arrow here is the flow, the development. This kind of thing, this is a development, right? I think it's the previous one. I think you guys asked me about like the here you see that I see SOC is just a portion of that. All right. This picture is very interesting because it will explain to you like how like the business are working, like how they make the chip and whatever. So this guy, the guy's IDM is go from the beginning, very beginning, all the way down here, right? This guy is called IDM, which is an integrated device manufacturer. Integrated because it has everything, integrated everything. This is Intel or like a Samsung. This one is the old model. You see that it's only like two guys here still have this model. So which means like before, Texas Instrument used to be the ADM. So they have from the process do everything until this. They design and do everything and they do the fab too, the foundry here too. Here's this portion is the foundry. Yes, it's a foundry here. So this one is a TSMC. Or like a TSMC or Global Foundry or like a Samsung too. Samsung do two. Samsung does two model. They have the model for the foundry and they have the model to do the whole thing here too. Whole thing. So the reason that this one is no longer like valid, I call that like in the dinosaur trend, because this portion, the foundry here is costly, very costly. And specifically for not poor country, but like developing country like Vietnam, this one like we have no chance. The reason is costly because you see that like each foundry of this, it's costing about 2 to 3 billion, and it has a lot of expertise to develop that. You see that Intel, the one thing is not like it's unimaginable is now Intel fall behind TSMC and Samsung in terms of technology. That's like unimaginable couple years ago. The reason for that is like the cost for this one is very high, and then like it need the focus. So this TSMC and Samsung is like this guy has only one job, which is to make the silicon. They have no idea about what the design is. They just make silicon. From here, I mean the mask right here. The interface between these two guys, like when design house here, right? So when you design, you have a layout design here. Now, this guy will take that mask. They don't care about what it is. They just take the mask and they go to the foundry and make the chip. That's all. So because they focus on that, the TSMC focus on that now, they beat out Intel. And then because it's focused on that, the cost is, but for them is like reduced a lot, and they like expert in that. This one like the model like IDM become dinosaur because of this, and the info cannot focus, so the company cannot do it all because of the limited resource. Even for Intel and Samsung, then put aside like Vietnam is like a way off that. So I just say like any idea to go to like the foundry is like fruitless. So this one is the IDM model. The next one is interesting is the lip house. This one is there should be like the lip house here. It means library house. It's to like differentiate with or from the design house. The design house here, and then you have the design house here is the fit very well with the I think what we can do in Vietnam for the like the labor source, like the level of education of like from like produced by the university in Vietnam. So which is we have the great material, we have the smart people, but we don't have the money to do this one. So we have to do this one so that like uh, okay, let me go back to the library house first. So the library house, it will take like the it will take the whatever like from like the characteristic from here, from like the foundry, and then they will build like the library house here is will make uniquely the things from processing device, which is here, this portion. They will be expert in like they take all these in and they will design those device, and then they will make the technology rule and they make the cell library, especially this one they will like make those cell library, and they will provide that to whoever, I think from like the foundry, right? From the foundry they will take like all the spec, all these spec, and they make this thing, and they provide that to like the next node, which is here, this one. Then I think the system spec here is like that one is the like the design spec. So which is like when you have a demand, you will have the spec, right? The spec will reflect like your demand from your device. So you have it. The problem with us, us is that we don't. The demand that we have is like very like primitive, like not much. I think let's say like the U.S. has demand to like with the satellite, with the like the social the security, cyber security, the demand for like for the chip in the phone and so on. So for example, like Qualcomm have a demand like they need to design a Snapdragon next generation, right? So they will define that here. But we don't have a Snapdragon. We don't have anything. So this guy, there will be some guy in US or like they have the some kind of device in mind. They will define that, and then they will give that to like from here to like they call this one is a design house. The design house is some customer will give a design house some idea, some system request, system spec, or like the device. It's not a device, design spec, and then they will turn that into like the logic device design here. This one is when the RTL get in. Okay, so the logic say they will like these two usually like go together. The guy who do the system design to like split that into data part and control part, and then after that they will write RTL, and they go like they combine these two. So usually system design and RTL go in parallel. So they will do that and then like do everything now. So this one is crucial to have a product, but we need the spec. Hold on a second. Okay, let's stop it. Okay, I think, sorry. All right, let me see if I can, oh, now it's blocked again. Okay. Okay, let me share again. All right. So the thing is, this model is for us, right? For us. The good the model for the fabless here, this one is Qualcomm. So they have the design, the spec, and they do all the way to here, but they still have to hand off to the fab here. See that? So all they did is they will design, they have the spec, they will design everything, and then they hand it off. So what they have more than what we have here is they have the spec. They know what they want to do. We don't know what we want to do because we don't have demand. So currently, actually in our program, we don't even have this one. So we don't have a knowledge in this one yet because we don't have the tool. So currently our tool, our software is at the mercy of the companies to give us, right? Because the EDA tool is expensive. If I think if we have the strategy for this kind of thing, we should invest some money for the software because our focus should be in here, which is you can see all the thing here is related to the software. Even you in this, people said a layout design is a physical layout design, right? But it's still we do everything here is about we use the tool, the software to design the chip. Only from this one and go out, it need the hardware, which is now we hand it off, whatever our result, we hand it off to TSMC or Samsung, you will make the chip for us. I think I talked with previously, we tried to do this one with the very outdated technology, which doesn't make sense because the very outdated, it does not cost much, it's not a very economic, and so on. So which is I think if we want a chance in catching up with the VSI design, we need to focus on this. Currently, we only have the tool for this one. Not even have a tool for that. We have only some tool for this portion. This one, 0. So going forward, I think if we can convince some kind of the high level whatever to invest something more here and something more here, then we have a chance. If not, whatever we have as an outcome, the student understand or learn something, I will be only to serve those company in Vietnam, the company that want to use the cheap labor in Vietnam. But if we want to develop something for ourselves, we need to have at least this. I think I cannot emphasize enough for that. All right, now I think we go to the flow. Yeah, I think now the flow. What is in the flow? So I think okay, sorry, I forgot the name. I think one student asked me where's the RTL is introduced during the thing. It's in here, and I explained that already. So now we go through the step in that, but still introduction is not detail. The detail will be later on in each chapter. Here we have a system design and logic design. Actually, the system design here, it would be this. Yeah, here. You have a system design, is kind of architecture design here. So it will split into structure, control, and data part. You have a control part and data part. A simple example for this is you have the memory, right? The memory, you have the input control as the read control, write control, and you have a multi-cycle control and so on. The data part is you have when you have a data part is from the input address and go to the output data, right? When you put the address to the address to input address, then with the read control like active, then you get the data out. When you put like a address to, you have like a write control like active, then you can write the data into the memory. So that means like that's a simple example for like the structure control and the data part. Then that's to explain like in RTL, and after you do that, you will transfer like you have that you will like convert those data part and structure control here. You convert that into what? Okay, this one is not clear. So you will convert that into like this. Here's the flop, and then you will convert here the data part. Here's the data part. You have a here's the signal, the clock signal, right? So that like every flop will be synchronized. Then you have those data part, and then you have the control signal here. You have it here, control signal go to here, right, and so on. So that means that here's the control signal, but the flop too, but also like a dosing is a control signal. Here is a data signal. So the RTL will describe this thing. We'll try to describe like this portion here too. They would describe this portion and also like define those flop. But you remember when I describe that, it just to describe this thing like describe that at many level, right? Behavioral level, you have a like and then you have a get level, or you have the even I can describe that in a transistor level. However, those description is just primitive. That's just like do like a plus b plus c plus d and so on, right? You have, let's say like they describe like this: a plus b like plus c plus d and so on. So this one, if you implement that, you have to like because this, if you use that, let's say you did plus d and plus e, like you have a 5 input here, right? You cannot implement that because here you have 1 2 3 4. You have the 5 input like all 4, right? Usually we don't use all 4. Sorry, this is all 5 input. Because the all 5, it means like you have the all 5 means you have this, the equivalent is like this. The all 5 is like this. 1 2 3 4 5. Okay, here. This one is a transistor. Okay, it's like a transistor. It's a P transistor, and here you have a 5 N transistor. Here's the N 5. Output is here, and then you have 5 input here. Sorry, I think I have this one is wrong. It's here 5 input, and this one like that connect to this. This one connect to this, and so on. So you have that. You see that this one is a long. This one is turned on. This one it's long like that and go out, right? When everything here is on, you have this one very long. So you don't want to do that. That's why I think even the description in the RTL is like this. You have to do the way like a simple way. Let's say you have to do this. You end these two, and then you all these two, and then you have now you have the all of this, and then you have now all 3 here. So because of it, you have now the thing is all 3. You have only like you become like that. It become like this, right? This thing, and then this one. I think let's say it's not this here. It's no. I think I put it simple. Yeah, right. It looks like you have a 2 stage here. Here you have like 1 stage, but this one even like the 2 stage, but it still might be faster than this one because this one is enormous. The delay here is very very bad, and it has a lot of trouble with the signal integrity. That I will explain later. So the idea here is whatever you define in the RTL here is far from optimum. That's why it need the I think here is missing. It need the in between here. I think let me okay, let me okay. So it needs the synthesis here. The synthesis here is job, as I explained before. It will convert, optimize, minimize, optimize, and then like mapping into the cell library to have a get netlist. So here you have then after you do that, because you convert the netlist, so we need to verify that. So it needs the verification here after synthesis. It needs the verification here before, and then so that this like it meet the requirement like functionality defined by here, right? Then I think there was question asked about RTL. Okay, I think question. Okay, so after that we have the logic. We verify that. After we verify everything, now we just give that to the PNR timing verification. This portion is called PD, as I said, physical design. The physical design, there's like a lot of steps in there, but I think this portion is a foundry. I think you don't need to know. All right, you can learn about that, but I think it's no use, because I don't think that we have any chance at the foundry at all, because currently the domination in the world is TSMC, Samsung, Intel. Even China is struggling with that, and they have that. They try to like make something, but they kind of like they are right now at the 28 nanometer technology, and Samsung and TSMC at the 4 nano and then 3 nanometer technology. So if you count, go from 28, go to 20, 14, 10, 7, 5, 4. So they are behind quite like 5, 6 generation. And they are, you see that China can send people to the moon, and then they can send the equipment to Mars. So they are very advanced, but it's still behind. So okay, this one is kind of you can read to see what it is, but I don't think that's like needed. Software design. This one is like the tandem, right? The tandem with the hardware design, which is you have, as I said, this portion is for the hardware design. But along the way, always remember that the design of the VSI is the tandem between software and hardware. It follows strictly that because of cost, PPAS. So again, the theory is that anything can be done by hardware and anything can be done by software. It's just if we want to balance between PPAS, that we have a choice. We can balance that when we have the work like the component. You see that, right? All the thing here along the way, software involved. So I think you get the idea. So that means that so along the way, the software will get involved into like a logic design, and this one. However, I think when it go into physical design, I think they miss it here. Physical design, I think is less. Is PD here? Yeah, maybe that. Okay, sorry. I think maybe like it means this here. Logic, it means like the PD inside here. However, like the PD is not like a logic design in this class, in this slide. It means like including the logic synthesis and also physical design. But usually people use the logic design is only the portion of synthesis. But whatever is not important. History of the LSI design methodology and this. Okay, I think this one is I think yeah, the history. I usually don't want to talk about much about history because this one is just like I want to talk about that when we have nothing to talk. Because this one is just like a FYI, right? For your information, it's not really doesn't really help much. It's just like for a chat. So which is this thing you can find anything. You can like find anywhere in the Google or like in the thing the web. So it's because I think actually it's from the 1980. That's the first time. Yeah, UMC actually. The 1980 is the first one. We have in the 1980 we have the first Intel. This one they talk about design methodology. Okay, so in the 96 we have Synopsys, TSMC, Cadence. I think this one is that missing between the EDA and from like this. Okay, design methodology is basically talk about the EDA, which is electronic design added. So this company is like they used to be you have sure we only have Synopsys, we have a Cadence, we have still a Mentor. Before that, we have a lot of things like a Magma. I think Synopsys, get it? We have I think View Logic. Synopsys, get it? Cadence here. I think you got a lot of things here. So those guys, a lot of company like doing the EDA. All the tools that we use from Cadence, from Synopsys, from Mentor Graphic, all those tools they call that in like an EDA tool. So I think, but now it like go down to like because when those guys view logic magma, right? So when they develop and they sell like good product, but they don't have enough resource, they don't have enough money to like go further. Those guys kind of compete and they try to and they bought it. They bought those things. So they have some. So they bought this thing. The Synopsys bought Magma or View Logic. The reason for that is two prongs, which is like first they bought a competitor so that they have no competitor anymore. That's the first thing. Second, they bought the knowledge. Whatever tool here, they have this, right? They have a knowledge here, so that means that this tool have because they compete with Synopsys. At the time, they compete in terms of like this one, they compete in terms of PD. So they bought it, so they get the knowledge from here to here. Then they integrate that knowledge into like the company. They just take whatever they want and they like throw away whatever it's not like compatible with the system. So that's the second reason. The third reason is that by the customer base, because this company has a customer, right? They have their own customer, which means like if they bought this one, now those customers go where? They will have to go to this guy. So the reason they bought it is because of it. The same thing. That's the way that how the industry works. And I think this one has nothing to do with the methodology. Ultra, this guy is about like the Ultra and Silence is the Ultra and Silence is about the FPGA, which is like a design house. They make the FPGA design, and then when they have the FPGA, they give to the foundry to make it for them. So it's kind of a design house. And this one is a standard product. It's not really a methodology or something. Old versus current design. Currently, I think this one, the C language here still like not synthesizable or like simulatable and verifiable. So only this and this. I think the VHDL, I believe that is in Europe. And Verilog is in the USA and elsewhere. It's very popular here. VHDL is not used in the US. And okay, those things. Yeah, I think this is the last. Okay, the example, as I said, you can read it as like a example because I think you can understand that because you already learned about RTL. So I think you can. But this one is an example. You have it would be like a long term or like a project in the lab, so that you can do it. But it's not like it's not the purpose of the lecture here, because we have no time to do that. So the last slide is this one. It's a from point of view of the design classification. Okay. That's why I want to explain to you what is the ASIC mean. The ASIC here, right? So now you know that, like, okay, from the customer, or like from the customer, right here. Then you have like customer give like you have design, go to RTL and synthesis verification, right? So this portion is like from the design, like whoever want the product, which is a customer. That's like a product. They go into here. So until here they have a out here. Yeah, that's right. They have a netlist, right? Now they have a choice. They want to do like the PD by themselves. They want to do PD by themselves, or they want to do that, and they have the mask here. So they have a choice that like they don't want to do that. Then they have the layout down here. It's called like the ASIC company. The ASIC company will take the netlist in, do the PD work, and get out the mask and give that to here is the foundry, right? So which is like the ASIC, because they have a netlist here, but it depends on the ASIC, right? Depends on the ASIC company. They will implement that, right? The PD here, they implement on silicon. Depends on how they implement that the PPAS will be different, right? That's why. And this work is kind of like as I said, this work is kind of like very quite difficult, and also like tiring. So that's why I think this one, the company like here they have Cisco. I don't know if you know, Cisco is the guy who do the communication equipment. So they will like do they design the router. They design the router. Then they design to this step only. They design from here to here. Then they give this one, this PD work to TI, Texas Instrument. They give this one to the ASIC department of TI. TI is Texas Instrument. Then when they get that to Texas Instrument will get the netlist, do the PD work, and get out the mask pattern, which is under the format GDS2. And then this one, they will go to like the foundry to do that. In the like 10 years ago, until 10 years ago, TI still have the foundry. So they will take the GDS2 here, they go to the foundry, their own foundry, and they make the silicon out here. They will like hand it off to Cisco. But you can see that the foundry now, TI now don't have the foundry for digital that much anymore. They don't do the ASIC anymore. Done. They just give up, and then they just shut down this department. Then because of the cost, still because they shut down right, as I said, they shut down the fab, the foundry. So this one, if they do only this one, there's not much like a benefit or money to make here. So they shut down the whole thing. That's why the ASIC the ASIC thing is kind of like done. So the thing is like that's why I talk about like our like a chance is to go from here. Basic design RTL is from here. We do the design how this portion. We do layout, and then we get the output, and we go to the fab. Go to the fab and go give that to them. All right, so that's why I try to explain the ASIC. ASIC is die down. So this one is from ASCP here. ASCP here, I think it depends. So we can go the way of the fabless, but only like as a design house. Until we have our like economy is up, and we have a lot of idea, a lot of demand from the inside, or like from the demand from customer, then we can do like this basic design, or like the spec system spec. But right now we have to develop from here. All right, I think that's all I have today. Okay, thank you, Professor Tin and everybody. If you have any question, just send me the email. My email, I think Dr. Professor Tin will send that to you. I'm
Yes.
happy that today I got some question. It's better than the other class. The other class I have no question. All right.
Yes. Thank you, Dr. Vic. It's very interesting lectures.
So if you have any question again, send me email, right?
Okay.
Mm. Thank you, and see you next time.
Yeah. See you.